Is this saturation? Is this in saturation or in trial? Let's first recognize this is an NMOS. That is very important. I've been telling you, make sure that you know what device it is. This is NMOS because of this arrow pointing out. And then I need to ask myself, where are the terminals? This is gate, this is drain, this is source. Not because of this terminal, because I see that this terminal is connected to 1.8 volt, and this is connected to ground. Why I want to identify them? Because then I need to use the equation I have learned. Okay? So is this in saturation or linear? It depends on this question. Is VGS minus VT larger or smaller than VDS? That is the question, right? If it is smaller, then I know that this is in saturation. But how do I solve it? I cannot solve it if I don't know whether it is saturation or linear, right? Because they have two different equations. So what we can do as an engineer is to do assumption. It doesn't hurt, right? We assume it is in saturation. You can assume it is in linear first. That is the same, right? If I assume it is in saturation, I know I can use this equation, IDS equal to W on L, mu C ox divided by 2, VGS minus VT squared. Instead of this one, I'm using this one because I assume it is in saturation. Okay? I assume it's saturation first, right? So from here, then I can start doing some substitution, right? I have W on L. I have mu C ox given. I have VT. How about VGS? W on L is 2 divided by 0.18. Mu C ox is 100 micro, right? And then divided by 2. What is VGS in this case? Yeah, but I hope that you know it because you see VGS is VG minus VS, okay? That's why you need to be very careful. And because I know this is S, I'm not going to say VGS is 1 volt minus Vx, right? That's why the terminal is important. VTH is given, okay? So these are just math. Let me see, I have the answer. Yeah.
At the end of this equation?
Oh, 1 plus lambda VDS? Okay, we are not there yet. That is the channel length modulation. So now we assume no channel length modulation. So yeah. So we just continue to use this equation for now, right? So I have the I, right? You just, you do it, right? Because I don't have it in my cheat sheet. Okay. Then how do I find the VD?
80 minus 5. 8 times 10 to the minus 5.
8 times to the 10 to the minus 5. So 80 microampere. You check it, right? I don't know, right? So what is VD? How do I find VD in this figure? You use this very often. Well, you can use Ohm's law, right? Because VD, ID is here. This is also ID, right? Right. So you can 1.8 minus Vx divided by 5K equal to ID. Or you just go for, I want you to be very familiar with this. I start with 1.8 volt, KVL. Then I go down, I have a potential drop. Then it becomes me, right? So this is 1.5 minus RD times ID. Potential drop is ID, right? Right. So if you plug in everything, including the 80 microampere that you need to check, what I got is 0.8 volts. Okay, basically Vx is 0.8 volts. Yes, I think, sorry, it is a typo. This is VDD is 1.8. I'm sorry. It's 1.8. Yeah. Okay. Maybe wrong, right? Yeah. So let's but I'm sure that my final result is correct. So let me erase this, right? So you calculate yourself. But I want to demonstrate the point is, now what is VGS minus VT? It is 1 minus 0 minus 0.4 equal to 0.6, right? And this is smaller than 0.8, which is VDS, right? So the assumption is correct, right? Because we assume it is saturation, so it must satisfy this equation. After I plug in, I really see that it does, right? So this is in saturation instead of linear. If you started with the linear, then you will see something contradictory. Then it can be either cut off or saturation. But however, it's pretty clear that this is on because VGS minus VTH larger than 0. Then you can say it must be in saturation. You don't need to do the calculation one more time. Right?
So should we always assume that?
In this case, I would assume that because most of the circuits are supposed to be in saturation. Yeah. Okay, here, this is not important, this calculation. I do want you to trace the node carefully and always remember VAB equal to VA minus VB. Don't mess this up. Do not assume VB is always 0 or you may get into problem, okay? Now, then we come to the channel length modulation that you were asking. And I keep asking you, do you agree with me? These two cases are exactly the same. And you already told me that, no, they are not. Yeah, they don't have the same height for this triangle. One is shorter. If I keep increasing the VD, this part will get shorter and shorter. So yeah, you have the same potential across it because on the left is the source, on the right is the point it just pinch off. And at the point it just pinch off, they must have the same potential as we said, right? Because when you just pinch off, you fulfill this criteria, okay? But it becomes shorter. So should the current be higher or lower for the same potential, but it becomes shorter while everything else the same? Shorter, remember this is a resistor. Shorter is what? You should have a less resistance, more current, right? Yeah. So in reality, you should see this going up. And this is called channel length modulation. This part is no channel length modulation. This part is with channel length modulation, right? So basically, the equation is still correct. You have I equals to W on L, but this L now depends on VDS. It's no longer constant, right? Because when I increase VDS, it gets shorter and shorter, right? But then the rest are the same. Okay? Now, but however, the community, right, or they think that this is not a good way to do the modeling. The good modeling is that instead of making the L dependent, they decided that why don't we add a term? I still keep L as constant, still the real L that you draw. Everything else the same. But then I want to add a term called lambda times VDS. right? So I have another term, 1 plus lambda times VDS, which achieve the same purpose, because when the VDS increase, the whole thing will increase, right? For example, the lambda can be 0.01 per volt. Now, this is something, if I ask you what is the unit, you will no one will remember, right, in the interview. But you should be able to guess, not guess, intellectually deduce. This is 1 unitness. This is volt. Something times volt becomes unitness. It must be 1 over volt, right? So there is a good way for you to show that you have this engineering thinking, right? Indeed, I was teaching another class, and then a student asked me a unit of a complicated equation, and I didn't know, and I'm nervous. I said, I don't know, let me check. But then I go back, I realized that I should use the same way to deduce and show them how to do it, right? This is the same. What is the unit of lambda? Forgot, doesn't matter. You frankly tell your interviewer, because I don't care, I forgot, but I can deduce. Because this is volt, this must be 1 over volt, so that you can add to 1. Right? If this has different unit, the equation will be wrong. Okay? And that's all I want to say. In summary, this is the new equation that we have. Still the same, but multiplied by 1 plus lambda VDS. I forgot to make it subscript. But the point is, this is still in saturation. So we start from linear, which is a resistor. Eventually, at saturation, when VD equal to VGS minus VTH, eventually, we hope that it is constant, but it is not. There's still a tiny modulation, and that makes the current source not ideal, right? Because now if I have a larger VDS, I have a larger current. Okay? Any questions? Okay, let's move forward. Let's take a look at how this lambda, the channel length modulation, right, related to the L. I already give you the answer. When I have a small L, small transistor, I do have larger slope, right, steeper slope. This one is more gentle, right? So for example, this one can be 0.0 lambda equal to 0.05, for example. And this one can be lambda equal to 0.01 when it is longer. Why is that? So lambda is talking about the channel length modulation, right? How much shorter it is when you increase the VDS. I increase VDS, look at this figure again. I keep increasing the VDS, the pinch off point go in, right? So my length, instead of original L, it becomes effectively L1, which is shorter. Now, if I start with a very long channel, you change the length by, let's say my channel was 1 meter. You change it by 1 millimeter. I don't feel it. It's only 0.1%, right? And that's why when it is long, I have less sensitivity to it. But if my transistor is 1 cm, you change by 1 millimeter, that is a big change, 10% of my original length, right? So you will feel a very big change in the current. So it has a strong channel length modulation. So this answers why in analog circuit, you will see people always have very long transistor. Why you're wasting the area? You're using the advanced technology. Why you're still using such a long transistor? Because they want to achieve a small lambda. When you have a small lambda, you have low output impedance, you have bad current source, bad gain, etc. Long ideal, yeah. So when it is longer, it's more ideal. Okay, so have this in mind, okay? So we also have other effects that we did not discuss, but we will not discuss. For example, what is the body? If you bias the body, the threshold voltage will change. Velocity saturation, and we keep saying that when the gate voltage is less than threshold voltage, it is off, right? That's not the reality. Nowadays, all the transistors, they are leaking maybe at 1 pico or even 1 nanoampere of current when it is off. And in Intel's chip, how many transistors you have? 1 billion. So you have 1 nanoampere leaking. If all of them are off, just sitting there is consuming 10 ampere of current. Okay? And that's why the rocket nozzle or the sun temperature analogy we talked about earlier, right? If they just keep scaling and increasing the frequency, eventually all the chip will melt. And that's why they become multi-core. And now they need the system level to control the chip. What they do is when this part is not working, they turn it off. What we call it dark silicon, and only turn on other parts. So in your iPhone, the chip, not every transistor is working at the same time. Okay. And of course, we only talk about every time just NMOS, PMOS, they can be combined together, becomes the CMOS technology, complementary metal oxide semiconductor that you need to know, right? Yeah, so I feel free to discuss. I claim myself, I spent many years in this area, so I should know this, right? So let's look at the one last example is this. I want you to draw the ID versus VIN. Now, when you look at this, don't jump into it. Don't dive right away. Understand the question first. What is the meaning of draw ID versus VI? Basically, I want you to plot a graph. It's just like in the experiment. You ask, okay, now I need to do an experiment. What I'm asked to do is I want to change the V1, and then measure the ID with this circuit. And then let's take a look what circuit is this. This is an NMOS. So I better start labeling. This is source, this is drain, this is gate, right? Do not feel that, oh, this looks like a source, right? But because this is NMOS, yeah. Good. Very good. Assuming V1 is less than VDD. Yes, we will stop there. Assume, so I should say that. Assume for this page, right? V1 is less than VDD. Very good, right? Otherwise, you need to swap the source and drain, or you are not going to get the right result. Okay? So basically, I'm asking you to pick a transistor from in the lab, connect the gate and the drain to VDD, turn it on, and then for the source, connect to a voltage source called V1. And then what? Start changing V1 from 0, maybe to VDD at most. Okay? And measure the current. Right? That's what you need to do experimentally. Right? Ask yourself what you need to do first. So now everything is clear. Right? And the first thing I can think of is I need to find the current, because if I know the current through here, then I'm done. This is the current I need to, right? But what equation should I use? This is a transistor. I have 3 possible situations. R equal to 0 when it's cut off, right? Linear and saturation. Here, I kind of confidence that when V1 is small, VDD probably is larger than 1, right? And also the question is asking linear and saturated. But it can be that I gave you a wrong transistor with very high VTH is always off. You can argue that, but now this is the class, not exam. Right? We don't need to argue on this. Linear or saturation. So the first thing I need to do is to check what is VGS minus VT compared to VDS. Right? And maybe I'm very confident. Let me just assume that this is smaller than VGS. I can do an assumption, right? But I put a question mark here. So all I need to do is do substitution. What is VGS? VDD minus VS minus VT, right? On the left-hand side. Do not think that, oh, I look stupid. Why I want to do this simple expansion? Do this. This one really help you a lot in the exam when you are nervous. How about on the right? What do we call it? VDS. Anyways, good. Someone also say V1. You can also do that. But if you do V1 here, you better do V1 here. Why is that? You see that they both have minus Vs, right? So they can get cancelled, right? VDD minus VT smaller than VDD. VT is positive. So VDD minus VT smaller than VDD. Is it true? Always true, sometimes true, never true? Always true, right? So that is always true. Then what does it mean? It means it's always in saturation as long as V1 is less than VDD. Because when V1 is larger than VDD, we need to swap the terminal of gate and of source and drain. Then we need to look at it carefully. But we're assuming V1 less than VDD. This one is always true. So this is in saturation, right? And you will find that it's always true because the gate is connected to the drain. We will learn again later, but this is always true because this is a so-called diode-connected transistor. The way it is connected, make it behave like a diode. This is a diode-connected transistor. We will study it again later. Is that okay? Okay, so with this, then I know what equation to use. The equations is going to be, this is 1, and this is 2, and then I will come here, sorry for this, 3. Then I know I'm going to use ID equals to W on L mu C ox divided by 2VGS minus VT squared. This is the right equation, right? Because it's saturation. So I need to plot ID, so I keep ID. W on L mu C ox, this is a parameter, I keep them. What is VGS? VGS is VG minus VS again, right? So VG is VDD. VS is V1. Okay? You won't come to here if you just jump directly unless you are very familiar with this, right? So I'm very careful in using my equation from the cheat sheet and substitute them one by one. Even VGS, so simple. I still call it VG minus VS, and then I say VG is VDD, VS is V1. Make no mistakes. So I have ID and V1 here already. Then I can plot it. Of course, when V1 equal to 0, I have a large current, right? This is ID equals to W on L mu C ox divided by 2 VDD minus VT squared, right? Because when V1 is 0, this is large, right? And eventually, when V1 equals to VDD minus VT, right? When V1 increase, eventually this is VDD minus VT, the whole term becomes 0. Yeah? I can do the same thing for others, but here I just want to sketch. This is what you will get. Okay? And why it is curving in this way, actually I did it wrong in the past, is because if you just try to plot it or you try to find the first derivative, you find that it's curved in this way instead of this way. Okay? But here I'm not going to test you this, right? So that is a way to sketch the curve, okay? I done what I want to say now. Any questions in all this line? We can discuss. No? Yeah, treat it as a tutorial, right? I did not follow my plan. I was hoping to go everything fast and then have like discussion like this. but it looks like difficult. Yeah, question?
Yeah,
Yeah, it's for still 1 minute for discussion. Everything is clear? Okay, then we can stop early today.
Over time, like